Hello, my name is Dave Brown. Today we start a new teletrain series entitled Industrial Pneumatic Technology, which is based on the Parker fluid power text of the same name. This course is designed to introduce you to the basic principles of pneumatics and to the components found in industrial pneumatic systems, as well as to help you understand their various applications. The material on these programs repeats much of the material of the text, but it is presented in a different way. And if you use the programs and the text together, you'll find that pneumatics is relatively easy to understand. Pneumatic systems, like hydraulic systems, work because of a special property of fluids, the special way that fluids transmit force and pressure. And we'll go into that in a few minutes. But first, let's define a few terms and take a quick look at the development of pneumatic power. A fluid is a substance which tends to flow until it conforms to the outlines of its container. If it's a liquid, like water, it will not necessarily fill the container. A gas, on the other hand, is a kind of fluid that has neither independent shape nor volume, but tends to expand indefinitely. That is, it takes the shape and fills the volume of its container. All gases are fluids, but not all fluids are gases. Oil, for example, is a fluid, but not a gas. Oil is the fluid usually used in hydraulic systems. Air is a gas and also a fluid. The term pneumatic applies to any gas, but as used in an industrial plant, it usually refers to something which is moved or worked by air pressure, or to something which is used in a compressed air system. So in this course, when we use the word pneumatic or the word gas, we will be talking about air. Okay, what is a pneumatic system? Quite simply, it is a system that can store and transmit energy in the form of compressed air. Another form of energy, usually electrical energy, is used to drive some kind of compressor. Then the air, under pressure, is controlled and directed by the system, and the energy which has been stored in it by the compressor is delivered to the place where it is needed to perform work. Man was born with one of the first pneumatic devices. Our lungs are actually small air compressors. When you exhale quickly, you are directing the compressed air up your windpipe to your lips where it can perform work. Lungs work pretty well for blowing horns or even powering blowguns, but they aren't really very powerful. And as new uses were developed for compressed air, new methods of compressing it had to be found. Bellows-type blowers were used to start and maintain fires on things like the blacksmith's forge as far back as 3000 BC. But there was little further development until the Industrial Revolution got underway. In the early 1700s, mechanical compressors were developed which could produce pressures of 15 pounds per square inch, or about 1 bar. Now, right here I better explain a bar. A bar, as you can see from the picture, is, got the wrong bar. Here we go. In our case, a bar is a unit of metric measure used in the International System of Units, or the SI system as it's called. It differs from the United States measurement of pounds per square inch. But if you ever need to convert from PSI to bars, all you must remember is that 1 bar is equal to approximately 14.5 pounds per square inch. In the text, you will notice that the illustrations and problems are given in both U.S. and metric terms. But to save repetition from this point on, we will use only the U.S. measurement. If metric equivalents are required, just check the text or U.S. to metric conversion tables. By the early 1800s, compressors could deliver air at a pressure of about 90 psi. And this allowed compressed air to be used in applications not practical before. About this time, studies were being made to dig an 8.5-mile-long tunnel through the Alps. It was estimated that it would take roughly 30 years to complete the project with manual drills. However, with pneumatic drills, the job was finished in 14 years. The tunnel was opened to traffic in 1871. This successful use of pneumatic equipment attracted wide attention, and many cities installed central air compressors to provide city-wide pneumatic power, similar to our present-day distribution of electricity. The most notable of these systems was in the city of Paris, France, where by the year 1891, 25,000 horsepower of compressor capacity was needed to supply the demands for compressed air. Many engineers of that day felt that pneumatics would become the prime source of power for both homes and industry. Many felt that another emerging source of power, namely electricity, had too many technical problems and wouldn't be successful. Of course, we know that neither of these ideas was totally correct, because today both have found their place in society and industry. While electricity has become the most common and convenient form for large-scale energy transmission, pneumatics has proven to be a very effective and efficient form of power for many commercial and industrial applications. Here you see a list of just a few of the ways that compressed air is used, from air brakes to conveyors, from drilling to spraying paint to stapling. And there are many other common applications, like a dentist drill or the lift at your local service station. Okay, now let's take a look at some of the basic principles of pneumatic systems and see how they work. Most of us are pretty familiar with the way a force is carried through a solid. When a force is applied to a solid, it is transmitted in one direction only. But in the case of a liquid, if we apply a force by means of a movable piston, this force will be distributed in the form of pressure, and the pressure will be transmitted equally in all directions, no matter what the shape of the container. This property of a fluid to transmit force equally in all directions was first discovered by Blaise Pascal way back about the year 1650, and is known as Pascal's law. For all practical purposes, liquids, like the oil in a hydraulic system, are incompressible, and their volume is not changed. But if we apply the force to a gas, the piston will move and compress the gas. As the gas volume becomes smaller, the pressure increases until it balances the force being applied. And at this point, as with a liquid, the resultant pressure is transmitted equally in all directions, no matter what the shape of the container. Okay, the gas is under pressure and contains potential energy that can be used to perform work. But how do we know how much pressure is available? It depends on two things: the amount of force being applied and surface area of the movable member being used to compress the gas. And since a piston, like this one, is the most common movable member used, we'll need to know how to calculate the area of a circle. As you probably know, the area of a square is equal to the length of one side times the length of the other side. As shown in our example, if one side is 10 inches long and the adjacent side is also 10 inches, then the area is 10 inches times 10 inches, which equals 100 square inches. Now, if we draw a circle within the squares so that it just touches the sides, then the diameter of the circle, that's the greatest distance across the circle, will be 10 inches. If we count the squares inside the circle and add up all the little pieces, we will find the area of the circle to be 78.54 square inches. Since the area of the square is 100 square inches, we can then say that the area of a circle will be 78.54 divided by 100, or 0.7854 times the area of a square the circle will just fit into. Another way of stating this is the area of a circle equals 0.7854 times diameter times diameter. Diameter times diameter is usually written as diameter squared. If the number 0.7854 is hard for you to remember, one way is to look at your calculator which will have the numbers arranged in a square, 7, 8, 5, 4. Now let's say we calculate the area of a piston and find it to be 10 square inches. And suppose we have a force of 1,000 pounds. How much pressure will be generated in the gas? The formula used to find out is pressure equals force divided by area. In our example, 1,000 divided by 10 equals 100 pounds per square inch pressure. In other words, the force on the piston, 1,000 pounds, is spread evenly over its area, 100 pounds on each of the 10 square inches. And then remember, this pressure is exerted in all directions through the gas. Okay, but air under pressure isn't much good unless we can use its potential energy to perform useful work. We must apply it to an actuator of some sort. The most common type of pneumatic actuator is the cylinder. A simple cylinder is composed of a tube which is closed at each end and has an air inlet and an air outlet and a movable piston with a rod connected to it. When air pressure is put in here, the piston has a force applied to it. And if the force is great enough to overcome the resistance of the piston, the rod, and whatever load is connected to it, then the piston will move. How do we calculate the amount of force that a cylinder will deliver? We just reverse the formula we used a minute ago. Now, instead of reading pressure equals force divided by area, it reads pressure in pounds per square inch times area in square inches equals force in pounds. For example, let's say we had 100 psi pressure and a 2-inch diameter piston. The 2-inch piston will have an area of 2 inches times 2 inches times 0.7854, or 3.14 square inches. In our force formula, force equals pressure times area. So 100 psi times 3.14 square inches equals 314 pounds of force. All right, now let's say we need more force, but our air pressure is still 100 psi. We can increase the output force by simply using a cylinder with a larger diameter. The larger diameter cylinder will have a piston with a larger area. If we use a cylinder with a 3-inch diameter piston, the piston area is 3 inches times 3 inches times 0.7854, or 7.07 square inches. And now, still using the same 100 psi pressure, the force will be 7.07 times 100, or 707 pounds of force. If because of space limitations or some other reason we're not able to go to a larger cylinder, we can get a larger output force by increasing the air pressure with something called a pressure intensifier. In simplified form, it looks like this. We have a large cylinder here and a small cylinder here, and their pistons are connected with a rod like this. If the large piston has an area of 20 square inches and there is 100 pounds per square inch pressure exerted against it, then the force in the rod will be 100 times 20, or 2,000 pounds. Now, if the area of the small piston is 5 square inches, then the pressure at the outlet here equals the force, 2,000 pounds, divided by the area, 5 square inches, or 400 pounds per square inch of pressure. Thus, with the intensifier, we have increased the pressure from 100 psi to 400 psi. You will note that although we have increased pressure, we really haven't gotten something for nothing. Over here on the 100 psi side of the intensifier, the volume is 4 times as great as the volume here on the 400 psi side. What we've done is traded volume for pressure. Now let's talk a minute about measuring pressure. There are two scales for doing this. First, we have the absolute pressure scale, which is labeled PSI-A. Then there is the gauge scale, which is labeled PSI-G. Gauge pressure plus 14.7 equals absolute pressure, and we'll explain that more in a moment. If only the notation PSI is used in identifying a pressure, such as 10 PSI, this is assumed to be PSI-G, or gauge pressure. A common pressure gauge, when not connected to anything, will read 0. This is a 0 gauge pressure. Actually, there is, at standard conditions, always 14.7 pounds per square inch pressure on everything which is exposed to the atmosphere. We don't normally think of air as having any weight, but it does. If we consider a cube of air a foot on a side, then that one block wouldn't weigh very much. But if we take thousands of these cubes and pile them up one on top of the other, then they would exert an appreciable weight, or downward pressure. This is just what happens in our atmosphere. The air extends upward for several miles. This pile of air is exerting a pressure on everything, on every rock, every plant, every square inch of your body. You can't feel it, but it's there just the same. Okay, how much pressure does this pile of air exert? One way to determine how much is to close one end of a glass tube and then fill it with mercury. Now we invert the tube in a bowl of mercury. Since the only thing that can balance the column of mercury is the pressure of the atmosphere on the mercury in the bowl, we can then determine, by the height in the tube, just how much pressure is exerted by the air which is piled upon the Earth's surface. As you can see here, the column of mercury is approximately 30 inches, which is what it's usually rounded off to. Actually, it's 29.92 inches at standard conditions and at sea level. If we tried the same experiment on top of a mountain, since we would be higher, there would be less air piled up above us. So the column of mercury, which would be supported, would be shorter. If we weigh 1 cubic inch of mercury, we find it comes to 0.491 pounds. So it will exert a force of 0.491 pounds on whatever it sits on. Therefore, 29.92 inches of mercury will exert 29.92 times 0.491, or 14.7 pounds per square inch. So the atmospheric pressure on the surface of the mercury in the dish is pushing back with an equal pressure of 14.7 pounds per square inch. As we see here, atmospheric pressure can be stated in either inches of mercury with dashes for inches and the letters Hg, which is the chemical notation for mercury, or in terms of pounds per square inch absolute, which is usually shortened to PSI-A. To convert inches of mercury to PSI-A, as we have just seen, we simply multiply by 0.491. To find inches of mercury when we start with PSI-A, we divide by 0.491. A rule of thumb is that 2 inches of mercury equals approximately 1 pound pressure. All right, this is a standard industrial gauge, and as you can see, it is reading 0. Now, as I just explained, it actually has 14.7 pounds per square inch pressure on it. But that 14.7 is exerted on the outside of the Borden tube as well as the inside, so the gauge registers 0 pressure. The pressure which a normal gauge reads we call gauge pressure, PSIG. To take atmospheric pressure into account, we must add 14.7 pounds per square inch to gauge pressure. And this pressure, which includes the atmospheric pressure, is called pounds per square inch absolute, or PSIA. The term vacuum is given to any gauge pressure less than standard atmospheric, and vacuum is usually measured in inches of mercury. This can be stated in either of the two ways you see here: inches of mercury absolute pressure or inches of mercury vacuum. 10 inches of mercury vacuum means that we have 10 inches of mercury less than atmospheric pressure. As we can see, the absolute pressure corresponding to 10 inches of vacuum is approximately 20 inches of mercury absolute. Since here, at absolute zero, there is a total absence of pressure, it is not possible to have a vacuum higher than 29.92 inches of mercury with standard conditions at sea level. Zero on a vacuum gauge equals atmospheric pressure at standard conditions, and the gauge measures how much less than standard atmospheric pressure is in the system. And the gauge is usually marked off, or calibrated as it's called, in inches of mercury. To explain vacuum a little better, let's look at this system. We'll use a glass tube set in a bowl of mercury again. As long as the top of the tube is open to atmospheric pressure, as you see, no mercury is forced up the tube because the pressure on the surface in the bowl is balanced by the atmospheric pressure pushing down inside the tube. Okay, now with a vacuum pump, we start to pump some of the air out of the top of the tube, which creates a partial vacuum. In this case, 10 inches of mercury. Now, since atmospheric pressure is approximately 30 inches of mercury absolute, and we now have 10 inches less here in the top of the tube, the atmospheric pressure pushes the mercury up the tube 10 inches. If we pump all the air out of the top of the tube, then atmospheric pressure would push the mercury up approximately 30 inches. As you have noticed, we have used a vacuum gauge to measure the vacuum. Exactly the same principle is used when you drink a soft drink with a straw. You create a partial vacuum in the straw, and atmospheric pressure pushes the fluid up into your mouth. This ends lessons 1 and 2. Now turn to page 14 in your text for the review exercises on the material we have just covered. I'm Dave Brown for Teletrain.